So hello everyone, I'm going to be talking about change of energy for the Change of Energy Lab. I'm going to be giving you all the details of the equations you'll need, the concepts you need to understand, and the data you need to finish off the experiment. So the main thing to remember in change of energy, well, the main thing to remember in physics is that energy is conserved always, always, always. All right? If an object loses energy in one form, it will either gain another or it will transfer it to another system. The main way this is done is obviously through friction, right? So if you have blocks sliding down a ramp like it did in the last experiment, it's slowed down. That loss in velocity turned into sound and heat, which in turn was the vibrations of the molecules in the ramp. For this lab, for this change of energy lab, we will be looking only at scenarios where there is no friction. So there's only going to be two forms of energy we're going to be looking at: potential energy and kinetic energy, right? So the change of energy overall is equal to the addition of the change of potential energy and the change of kinetic energy, and this is zero if there is no friction. Okay? So in other words, the change in potential energy is equal to the negative of the change in kinetic energy, or vice versa, right? So for this lab, you're simply looking at carts going down a ramp. We'll be showing you some footage here of two carts going down two different ramps. As you see, as the carts go lower, they speed up. That change in potential energy, which is reduced as the carts go to a lower altitude, turns into kinetic energy, the carts speeding up. So here I have recreated the Blinky diagram of the carts rolling down the coaster. You will have a handout of this available to you on Canvas, which you will use to finish off your experiment. I've tried to recreate this reliably from that handout, and this illustrates the relation between change in height and change in velocity. So now this relation between change in height and change in velocity does not depend on either the path the object takes or the mass of the object. We'll be showing some videos on the screen. First of the same cart going down two different paths down the coaster. You should be able to tell that the cart has the same velocity at the end when it's given the same starting velocity to begin with. Right? And so this is because the potential energy only depends on the height. No matter what path you take, no matter what kind of crazy roller coaster you went on, it only depends on what the difference is between the starting height and the ending height. That's the only thing that determines what your change of potential energy is. Okay? So now to get into why the mass does not influence the change of velocity. So we'll again be showing you some videos on the screen now of two carts of different masses going down the same path. You should be able to see that they have the same velocity at the end. Right, to show you why the mass does not depend, I'll actually derive the relation algebraically. So we'll say, use this relation. So I'll say negative change in potential energy equals a change in kinetic energy. And so we have negative mgh delta h equals 1/2 m delta v squared. So the delta h is this here. So delta h is going to be negative. This minus sign makes it positive. That's important because we're going to be taking a square root here. But before that, we cancel out the mass. So immediately mass cancels it out. And so we get delta v equals square root of 2g negative delta v, delta h, right? And so the change in velocity is only dependent on the change in height and the gravitational constant. So the thing to remember here is that this relation holds along any point along its path and along any time frame. That's because this holds along any point along its path along any time frame. The change in energy is always zero throughout this entire thing because energy is always conserved. Any change of potential energy goes directly to kinetic energy, and any change in kinetic energy goes directly into potential energy if there is no friction drawing energy out of the system. Okay? So the other thing to remember here is for this, we're only really focusing on the change in height, not the absolute value of the height. So that means we can place the origin, the place where we simply say height 0 and potential energy 0, at any point along this path. However, the most appropriate places to put them are either at the very top of the path, so we can say that, or we can put it at the very bottom of the path. Right? So height goes 0 there. Either is valid, and both will give you the same result for the change in velocity. Kinetic energy is different because you're always going to have the kinetic energy being 0 here because the velocity is 0 at the start, and you have kinetic energy being defined very precisely at every point because you have velocity being defined very precisely at every single point along this path. Okay, so potential energy, you can determine where it's 0 and simply use a change in height relative to that point. Kinetic energy, you cannot. Kinetic energy, you need to define it based off the velocity at that point. So the last thing you will need to finish off your experiment is this bar diagram to visualize your kinetic and potential energy. So here I've labeled points A and points B here. Can be drawing the relative potential and kinetic energy. So I've defined potential energy to be 0 at the top. So say here at point A, the potential energy should be negative, right? And the kinetic energy should be positive. And since the change in energy should be 0, since the change in energy should be 0 throughout this entire process, and we define potential energy to be 0 at the start, they should be equal and opposite. So we have a small negative potential energy here, and a small kinetic energy there that's positive. All right, and we go down to B. You see the velocity is clearly higher, but also the potential energy is also more negative, right? Because it's further down from the reference point. So we can draw it here. Kinetic energy is much higher. Potential energy is much lower, but they're equal in magnitude. Again, keeping with this relation. Okay? If I redefine the reference points of potential energy being 0, say at the bottom, I would have to redraw these graphs, and the sum would not be 0. Rather, the sum would be the sum should be equal to the potential energy at the very top. Okay? So keep that in mind when you go on to finish off the last section of your experiment. That should be everything you need to understand this. If you have any questions, ask your TA through Zoom or whatever stream service we decide to use.